All right, for problem number 4, you notice that I have a negative out front. So when this happens, we're going to treat this as also having a GCF. And we're going to say that in this case, the GCF is -1. So the first step, I'm going to factor out a GCF of -1. That is basically going to change the sign of each of the terms in the original. So I get positive x squared, positive 2x, and -15. Alright, so now that we have a equal to 1 again, we will identify that c is -15 and list the factors. So we could have 1 times -15, -1 times +15. 15 is not evenly divisible by 2. It is evenly divisible by 3. So we could have 3 times -5. We could also have -3 times +5. And again, if you keep going, you're just going to get repetitive factors from here. So now we're going to switch to trying to determine which pair will give me b equal to +2. And of course, if I do 1 plus -15, that's not going to be it. -1 plus 15, that's not going to be it. 3 plus -5 is -2, so that's close but not it. The next one, -3 plus 5, that's going to be our winner. -3 plus 5 is 2. So if I go back to my original again, remember that the first thing we did was factor out that GCF of -1. Now we can write our trinomial as 2 binomials, where each of my first factors is going to be x, and we determined that we need -3 and +5. So we'll have x minus 3 and x plus 5. And again, you can multiply that back out if you want to verify that you do get the original problem when you multiply out that factorization. Now, number 5 is a little bit different because you see this time we have 2 variables, not just one. We have an x and we have a y. So every time we got a squared term before, most of the problems we did were x squared, is we ended up multiplying x times itself to get x squared. So this time, not only will the factors in the first positions in the binomials have a variable, but the ones in the second positions will too. So we don't really have to have a different strategy for this. My c in this case is -21. We're still going to list out the factors. So it could be 1 times -21, -1 times +21. 21 isn't divisible by 2, it is divisible by 3. So we could have 3 times -7, -3 times 7. And I think if we kept going, they're going to start repeating from there. And we're looking to get a b equal to 4. So from looking at this, we know 1 plus -21, that won't be 4. -1 plus 21, that won't be 4. If we look at 3 plus -7, that's -4, so it's close. The last one, -3 plus 7, that's the one that gives me 4. So if I go back to my original, x squared plus 4xy minus 21y squared. We didn't have to factor out a GCF this time. So I'm going to go ahead and set up my two binomials. It starts off the same way as the others. We still know this has to be x and x. We know that our numerical factors are -3 and 7. So I'm going to have -3 and +7. But unlike the previous problems, if I multiply those two binomials back out, they're not going to have the y variable. So we can't just have -3 and +7. We have to have -3y and +7y. Now that is my complete factorization. Alright, so the next couple that we're going to look at, these are going to have an a that is not equal to 1. So you can still use trial and error on these, but it's more difficult, and it gets increasingly difficult as the a, or that very lead coefficient, if it has more factors. The first one is 2, so we only have factors 1 and 2. But think about instead if that number was something like 12. Then you have 1 and 12, you have 6 and 2, you have 3 and 4. There's a lot of different things that it can be, and we start to get a lot of different options that we have to try out. So when a is not 1, most of the time we'll go ahead and switch to using what we're going to call the AC method, and then we can use factor by grouping that we learned earlier. So I wrote in my standard form again over my given problem, ax squared plus bx plus c. So the AC method is called that because the first thing we're going to do is find AC, or a times c. And you see in this case a is 2, c is 14, so a times c is 28. So what I'm going to do is list the factors of 28 this time. So not just the c, but what I get when I multiply a times c. So the factors would be 1 times 28, 2 times 24. 28 is not evenly divisible by 3. It is evenly divisible by 4. And then if we kept going, we're going to start getting repetitive factors again. So that's as far as we have to go. Now the next part is similar. We still want to know which set of those factors that we just listed will give us the b, which in this case is 11. So 1 and 28, 1 plus 28 is not going to be 11. 2 plus 24 is not going to be 11. So I know that 4 plus 7 will be the factors that I need. What's different is the next thing we're going to do is rewrite the original trinomial using those two factors for b. So the original was 2x squared plus 11x plus 14. We're going to rewrite this b term using the factors 4 and 7 that we just found. I'm going to write 11x as 4x plus 7x. The 4 and the 7 are the two factors we just found that multiply to 28 that will add to 11. If you see what we've ended up with, I now have a polynomial with 4 terms. And if you think back to the previous lesson, when we had 4 terms, we used grouping. And remember, we just grouped the first 2 and grouped the second 2, and we factor a GCF out of each pair. So if I look at just the first 2, 2x squared and 4x, they have a GCF of 2x, so I'm going to factor that out. That will leave me with x plus 2. Then there is a plus sign. And then the 7x plus 14, the GCF is 7, and that also leaves me with x plus 2. And remember, this is what we said had to happen. We have that common factor of x plus 2. So we're going to bring that common factor out to the front. And then if that's gone, what's left is the 2x plus 7. So this is the factorization for 2x squared plus 11x plus 14. All right, let's look at one more of these. So the next one, I have 8x squared plus 18x plus 9. 8, 18, and 9 don't have any common factors. So since a is not 1, we're going to start off by finding a times c again. So a is 8 and c is 9, and 8 times 9 is 72. So we're going to start listing the factors for 72. So the first one is 1 times 72. The next one is 2 times 36. The next one is 3 times 24. The next one is 4 times 18. 72 is not evenly divisible by 5. The next one is 6 times 12. It's not evenly divisible by 7. The next one is 8 times 9. And if we keep going, the factors are going to start repeating again at this point. Alright, so now that we have our factors of 72, we need to know which pair will add to 18. So you can look through your list again. We know 1 plus 72 is not going to work. 2 plus 36 won't work. 3 plus 24 won't work. 4 plus 18 won't work. The one that will is 6 plus 12 is 18. So back to my original, 8x squared plus 18x plus 9. We're going to rewrite that middle term using the factors of 6 and 12 that we just found. So instead of writing 18x, we're going to write 6x plus 12x plus the 9. And then we're going to pair them off and do factor by grouping again. So my first two terms, 8x squared and 6x, those have a common factor of 2x. So I'm going to factor that out. That's going to leave me with 4x plus 3. My second binomial, 12x plus 9, that has a common factor of 3. So I'm going to factor that out. And that also leaves me with 4x plus 3. So then the last step is to factor out that common binomial. And then what's left over is the 2x plus 3. So this is my factorization. Alright, the next ones that we're going to look at are what we call special products. And we call them special products because if we recognize what we're given as one of these special products, then factoring them can be a little more simple. So you remember we talked about when we were multiplying a difference of squares. So we found out if we multiplied a minus b times a plus b, that the middle two terms were opposites and canceled each other out and left us with a squared minus b squared. So of course, if we're factoring, we are looking at this in the opposite order. We're going to be given the a squared minus b squared, and we're going to factor it into a minus b, a plus b. So if I have x squared minus 9, the first thing that I'm going to look for to recognize that this is difference of squares is that I have two terms. If there are three, it can't be difference of squares. And both of those terms have to be perfect squares. And of course, from the name difference of squares, it does have to be a subtraction. There is no factorization for sum of squares. Okay? So if you look back at the generalization, a squared minus b squared is equal to a minus b, a plus b. So a is the square root of a squared, and b is the square root of b squared. Or you can look at it as, what did I multiply times itself to get that? So if I have x squared minus 9, what I had to multiply times itself to get x squared is x. X times x is x squared. So that means that my a would just be x. And if I have 9, what I have to multiply times itself to get 9 is 3 times 3. So that means my b would be 3. So if we just want to fill in the formula, it's a minus b, where a is x minus b is 3, and a plus b, x plus 3. So this is the factorization. And again, note, if you multiply that binomial times that binomial, you are going to get x squared minus 9, the original problem, back. Alright, the next couple that we're going to look at are going to be important later when we start looking at quadratics, and we're talking about perfect square trinomials. So we talked earlier about squaring binomials when we talked about multiplication. We said if I had a plus b squared, that was the same as writing that out twice. And if you full distribute or use the box, you would get a squared plus 2ab plus b squared. And it's 2ab in the middle because having the exact same two binomials, those two middle terms are always exactly the same, so we end up with two of them. So if I look at x squared plus 6x plus 9, the first thing is we would need to recognize that that particular trinomial can be written in this form. So how do I recognize that? One, we got to have 3 terms this time. The first and the last terms must be perfect squares. And they are. I have x squared, that's a perfect square. The last term is 9, that's a perfect square. And then the final thing that has to be true is that middle term, the 6x, has to be 2 times the a times the b. So remember, just like the last problem, if I have x squared, the a is going to be x, because that's what we have to multiply times itself to get x squared. And the b is going to be 3, because that's what I multiply times itself to get 9. So if I plug that in, 2 times a, which is x, and b, which is 3, 2 times x times 3 is indeed 6x. So we know that this is a perfect square trinomial. So once we know that, we don't have to use trial and error or the AC method. We know that it's just going to be the same binomial times itself. So both of the first two will be x. This one is plus, so it'll be plus. And then it's b. And of course, if you want to write it like the formula, having the same binomial times itself is just x plus 3 squared. Notice for number 3, the only difference is the sign in the middle. So this is the second case of the square of a binomial where it's going to be a minus b squared. All of the information that we looked at for number 2 is going to be the same. My a is x, my b is 3, and if I multiply 2 times the x times the 3, we do get 6x in the middle. So the only difference this time is instead of getting x plus 3 squared, we're going to get x minus 3 squared. All right, number 4. This one looks a little harder. It's going to be a little more difficult to recognize as the square of a binomial. I still have 3 terms. The first term is a perfect square. 4 is a perfect square because of 2 times 2. X squared is a perfect square. And we know 9 is a perfect square. So if I want a, it's what I would multiply times itself to get 4x squared. So that's going to be 2x, because 2x times 2x is 4x squared. The b is going to be 3 again, because 3 times 3 is 9. And then we need for the middle term to be 2 times the a times the b. 2 times 2x is 4x, times 3 is 12x. And you see that matches the middle term. So all I have to do to factor this, because it's a positive case, we know it's going to be a plus b squared.